All right. Okay. Yeah, I'm sitting outside. It can be a bit noisy. Sorry about that. Yeah, I think. Well, today I'm going to continue some introductions to pulsars and pulsar stuff. So I think I will try to give a very brief introduction to pulsar timing. Yeah, to people that are not working on pulsars. Well, I think this is probably one of the most important thing to understand pulsar astronomy. Um, yeah, so I think I would try to cover all these four items, but I will be focusing mainly on the second one, and maybe in the next talk I will probably try to talk a bit more about what kind of science you can do with pulsar timing. But anyway, today I think I will try to give an introduction to actually the pulsar timing techniques. Okay. Well, I hope everyone is familiar with what is a pulsar. Um, they are basically highly magnetized, fast rotating neutron stars. Here I'm showing the first detection of pulsar signal by Josephine Bell. But I think the important thing is the rotation of neutron stars are extremely stable because of the compactness of the star, which makes them a very good timer and which makes pulsar timing very powerful to probe a range of physics. All right. So I have shown this before. So this is the so-called PP dot diagram. It's basically well, probably the most important diagram in pulsar astronomy, showing you different population of pulsars. Um, on the, yeah, in the left-hand side bottom corner, we have these so-called millisecond pulsars. So they are very old, fast spinning pulsars, and they are also the best clock probably in the universe. But as you go kind of like upper right, you move into sort of young pulsar territory. So where the magnetars and the high magnetic field pulsars are living. Okay. Um, so why this sort of relevant to pulsar timing? Um, so so basically what's happening is when you talk about pulsar timing, is kind of different for different population of pulsars. For example, when we talk about pulsar timing with young pulsars, we are mostly talking about, for example, detecting pulsar glitch, which is a sudden change of the spin period of pulsar. As for example, I'm showing here in the second panel of this, well, actually, in the first panel of this, the top panel of this plot, where you can see here, close to the dashed line, you have a sudden jump of the spin frequency or the spin period of the pulsar. So that's a pulsar glitch. And also, we can also do study timing noise of young pulsars, which, well, we don't really understand, but we believe is related to the, for example, the stability of the rotation of young pulsars. And obviously, if you look at so-called magnetars and other pulsars with very strong magnetic field, you can use pulsar timing to estimate, for example, the strength of the magnetic field and to study the coherent emission from these very extreme objects. So these are all about we call young pulsars, okay? And then, as I just showed in the previous slide, we also have a population of millisecond pulsars or old pulsars. So these are the pulsars that we can do very high precision timing. So this is also what people are mostly talking about when they talk about high precision timing. So through timing of these millisecond pulsars, we can, for example, measure the mass of neutron stars, and then from that we can understand the structure and the state of mass inside the neutron star. We can also test gravity series if a millisecond pulsar is in a binary with either another neutron star or white dwarf. And of course, you probably heard of gravitational waves. So we can use something called pulsar timing array to detect and study ultra low frequency gravitational waves, which I will talk about a bit later. Okay, so these are the basically general ideas about pulsar timing and what we can do. So if we go back to the questions, what is actually pulsar timing and how do we time a pulsar? The answer is actually quite simple. So let's assume we have a data set from a large radio telescope pointing at a radio pulsar, and if you ignore all the complicated stuff, this is probably what you would expect from the telescope. So the x-axis is time, and the y-axis is, let's say, flux density. So you have this train of pulses from the pulsar, and of course, for the real data, it will be much more noisier. But here, this is a very bright pulsar. So when we talk about timing a pulsar, so the first step is basically to measure the pulse time of arrival. So basically, when this pulses arrives the observatory or the telescope. So obviously, if you have a pulse like this, the easiest way to actually measure this is to measure the arrival time of the peak. So try your best, find where the peak is, and then write down the time of the arrival. Okay, so that's the first step. And then the second step is once you have all these time of arrivals or TOAs, so for given pulsar or neutron star, because we know their, for example, spin period, we know where they are, and we know for example, the time derivative of the spin period. So you actually have a pretty good model of the arrival time of the signal, basically. But obviously, the model is not going to be perfect. So there will be difference. So the second step is to compare the measured time of arrival with the prediction from your model or the timing model. Okay, so that gives you what we need for the third step. So that gives you, we call timing residuals. So this is what I showed in this plot. So the red dashed lines are the prediction from your timing model, and all the RI plus 1 and plus 2 are the timing residuals, basically the difference between the measured one and your model. And everything about pulsar timing is basically to understand the difference. So why there are actually difference between the measurement and the model. So if we, for example, for given pulsar, let's say we observed this pulsar every day for the last 10 years. So we have all this measurement of the pulse time of arrivals, and we plot the so-called timing residuals, the difference between your measurement and the model as a function of time. So this is what you will get for this particular pulsar. And what you can see is not white noise. And you definitely see some structures in the timing residuals. So what this tells you is, first of all, your pulsar, your timing model is not perfect. So there are something in the data that we don't understand. Okay, so for example, it could be intrinsic, as I mentioned earlier, to the pulsar. For example, the instability of the rotation of the pulsar. It could be because of the interstellar media. When the radiation from the pulsar travels through the galaxy, something might affect the arrival time, right? So this structure in the timing residuals can be the interstellar media, or it can be actually gravitational waves, because your pulsar will be constantly affected by the gravitational waves. So this is what I basically try to explain. So everything about pulsar timing is basically to understand all these structures and signals in the so-called timing residuals. Okay. Right. So the previous plot is timing residuals as a function of time, but we can also plot timing residuals as a function of frequency. So in this plot, we have very wide frequency coverage from 700 megahertz all the way to 4,000 megahertz. And again, as you can see, the timing residuals, they don't look flat around zero. They are not white noise, right? You obviously you can see at low frequencies, the arrival time deviate from the your timing model more than at higher frequencies. So what this tells you is there are some radio frequency dependent noise or things going on in your data. So this example I'm showing here is because of the dispersion measure is wrong. So we didn't correct for the dispersive delay very nicely. So this is the leftover signal. So if we take one step back, so let's say if we have a perfect timing model and we have perfect measurement of timing noise, so what would you expect this plot to be like? So you would expect all the data points are scattering around zero, and you would expect that the error bar of each measurement is comparable to the scatter. So basically, you expect the timing residuals to look pretty much like white noise. Okay, so this is what I emphasized here. So the TOA, the error bar of the TOA, base tells you the uncertainty in the measurement, and it should be, well, in a perfect world, it should be comparable to the deviation from the timing model. But if you see anything that's not white, it means there are some actually signs in your data. So that's the simplified version of pulsar timing, and obviously you would expect in reality this is much more complicated. First of all, the most important assumption goes into this whole timing business is that the pulse profile is stable. So you don't expect the shape of the profile to change as a function of time. If it is changing as a function of time, you would expect that that will cause problems or variations in your timing residuals. And secondly, the pulse profile can be more complicated than just a single peak. For example, here I'm showing the profile as like 2 peaks. So to measure the TOA is a bit more complicated than measuring the, well, where the peak is, because you have to take the shape of the pulse profile into consideration. And in reality, many pulsars show very complicated pulse profile. So the method we use here is called template matching, as I'm showing here. So you have a denoised perfect, we call template of the profile, and then you try to cross-match that with the observed or measured profile in order to measure when the pulse arrives. Okay, so it turned out a really clever way to do this is actually in the frequency domain rather than in the time domain. If you are really into this Taylor 1992 paper is probably one of the most important paper in pulsar astronomy, where this frequency domain template matching business was developed. But anyway, so in the frequency domain, it turned out that if you cross-match the template with your profile, the precision of your measurement are not limited by the time resolution of your data, which is exactly what we want. And the uncertainty of your measurement is purely determined by the signal to noise ratio, which is very, very neat. Okay, so that's basically the whole idea of pulsar timing. So one example of the application is so-called pulsar timing array. So let's think you have a bunch of millisecond pulsars in the Milky Way. we are here on the Earth, and you have different millisecond pulsars in all different directions, and they formed an array of millisecond pulsars. And then, if we have gravitational waves in the space and time, that's basically sort of all these wobbles in the space and time. You would expect that the arrival time of pulses from all these millisecond pulsars will be affected by the wobble in the space and time. And for certain types of gravitational waves, you would actually expect that all these kind of the deviations caused by the gravitational waves from different millisecond pulsars are correlated. For example, if you talk about gravitational wave background, you can actually analytically calculate what the correlation between different pairs of millisecond pulsars are. And if you observe a bunch of them for long enough, you can actually calculate the correlation and then compare that with the model predicted by the gravitational wave background. And this is basically how people are detecting ultra low frequency gravitational background with pulsar timing nowadays. So at the moment, we have a few pulsar timing arrays around the world. For example, we have the North American Nanohertz Observatory for Gravitational Waves, NanoGrav. Obviously, we have the Parkes pulsar timing array, one of the first timing arrays in the world, and we have the European timing array, pulsar timing array. And recently, we have the new MeerKAT timing array, and also the Chinese and Indian pulsar timing array. And if you combine all of them together, you have this so-called international pulsar timing array. So the motivation for the international pulsar timing array is basically try to observe as many pulsars as possible. So we want pulsars in all sorts of directions in order to, when you calculate the correlation, you cover the all different angular separations. And then you want to observe the millisecond pulsars or time them as precise as possible. So you want to use all the big telescopes around the world. So in the end, the goal is to combine all these efforts and create a data set so that we can actually confidently detect the correlation caused by gravitational waves, and hopefully in the future study the gravitational wave background. Okay, so a little bit about current recent development. So I think for pulsar timing, one thing to point out is the bandwidth of your observing system. As I mentioned in the second slide, pulsar radiation are wideband. So you want to observe pulsars with bandwidth as wide as possible. So the Parkes ultra wideband low receiver is one of the obviously one of the first and also one of the best system in the world at the moment. It covers a very wide frequency range so that you can actually increase your signal-to-noise ratio, but also to characterize the frequency-dependent noise in your data. So here I'm showing the full bandwidth of the ultra wideband low, and all the shaded regions are the legacy old systems, and you can see the frequency coverage is much better. But bandwidth comes with a price. So once you observe a pulsar with a very wide bandwidth, you start to realize that the profile becomes frequency dependent. So it's not stable anymore. So for wideband system, this is something you need to actually correct for, and this is one of the key things actually currently going on with high precision pulsar timing. And another thing is the interstellar media. So I'm showing one pulsar 1909 minus 3744. So here I'm showing the intensity of the pulsar as a function of frequency. And you can see this very nice scintillation happening as a function of time. So sometimes the pulsar is bright at high frequencies, but sometimes it's bright at low frequencies, and that can cause problem for your high precision timing. And finally, just want to briefly mention this. We have gone so far in pulsar timing, and people developed a lot of softwares, and especially in recently, we move into the Bayesian business. So we have all this Bayesian based gravitational wave detection algorithm and softwares, and they becomes very complicated. So I think the last thing I want to mention is pulsar timing used to be computationally very cheap, but this is not true anymore. Because of all the large data sets, a lot of TOAs and multiple telescopes, and the complicated Bayesian algorithms, pulsar timing actually becomes computationally expensive. So that's something challenging for the near future and for the SKA. Yeah, I think that's all I want to talk about. Happy to take questions if there are any.
So I have a question. So regarding you said you're searching for pulsar in all directions. So the distance is important here. So because they are not at the same distance, these pulsars.
Yeah, so the distance is not going to be actually a big problem. So all we care about is the direction. So you want to cover different RA and DAC. The pulsar can be either close by or farther away, and that's okay as long as they cover different sky area.
How old is the oldest known pulsar?
That's a good question. So all the millisecond pulsars are very old. They are like tens of giga-years, and that's because of the so-called recycling. So they are already dead after probably million years or something, and then because of the accretion from the companion, they got spun up and they become radioactive again. So the millisecond pulsars can be very, very old, at least a few giga-years old.
Any more questions? So how far away are we from, and that's a very difficult question, but really digging down into the gravitational waves with pulsar timing?
Oh, that's a really good question. Well, if you noticed the last year, actually, the Americans, the Nanograph, they actually published a paper claiming that they detected some kind of like 2 sigma signal from the gravitational wave background, and there are a lot of debates around that, whether that's actually gravitational wave signal or other timing noise. I think we haven't really agreed on that yet, but I think that shows at least at the moment we start to see some really interesting signals. I think people always predict we will be detecting gravitational waves in 5 years. So yeah, so maybe in 5 years.
What's going to be required to detect them? Is it just more data, or is it better data or better algorithms?
Yeah, I think ideally both. So you need both the baseline of your timing and also the precision. And actually, you also need the number of pulsars. So you want to observe as many as possible for as long as possible, and well, obviously as precise as possible. And it's really hard to tell which one is the most important. People have done simulations on this. For example, for given telescope observing time, some people claim that you want to actually observe many pulsars as possible. You probably don't really want to get very precise TOAs, but you want to actually cover as much sky area as possible. But I guess the short answer is ideally you want to observe them long and also precise.
Very good. All right. Thanks, Xi.
Nice.
Very good intro. Thanks, everyone. We will see you all next week. Thank you.
Bye.